Due to the technical problems, we have stopped our lesson in the simple loops part. We have learned that in finding the growing rate of some algorithms, we can ignore multiplicative constants, and the answer will be only ON here. Next example is nested loop. As you could see here, we have some constant time for execution of this expression, and this for executing the first loop, inner loop, we will execute it n times, and for outer loop also we will execute n times, and the execution of inner loop will be done so much times as the execution of outer loop. It means that to learn the time complexity of this nested loop, we multiply the constant for the expression, and this is for inner expression, and second n, which is for outer expression. Then the time complexity for our algorithm will be constant time n squared, or O n squared. If in the repetition in the nested loop, the execution time of inner loop, for example, will be some kind of I times, and execution of outer loop will be n times, then in this situation, how much time it will be performed? First time it will be performed some kind of constant time. Second, when I will become 2, it will be 2 constants. Third, it will be 3 constants, and so on, so on. So it will be done n times c times some constant time. Now, when we add all these execution times, as you remember from the formula before, the addition of numbers from 1 to n is n times n plus 1 over 2. Also, we have the multiplication to a constant, then the answer will be c times n times n plus 1 time over 2. When we simplify it, we understood that the all c over 2 will become some kind of constant of n squared, and this will be on the n notation, which is less than n squared. Then the answer also will be n squared times. It means that it doesn't depend how much time is it in the I. The worst case for this will be ON squared. Look here, but in this nested loop, the inner loop, we know exactly how much time it will be performed. It will be performed 20 times. Then execution time of this nested loop is 20 times some constant times n. Then the complexity of this nested loop will be ON notation, not ON square notation. This is because we know the how much time the inner loop will be executed. Let us assume that we have here some kind of sequence. It means that here we'll have one loop and then second nested loop, and these loops are not nested. It means that the first is separate, the second nested loop is separate. To execute the first, we spent 10 times constant. For execution of second, we spend 20 times constant times n. Then the biggest term in this polynomial is n, 20 times constant times n, where not writing these constants, then the answer will be ON. Here we have some kind of selection example. We are selecting some kind of from list, some kind of E. Does it contains this E or not? And printing it. Else, we are performing here some kind of loop for some kind of object. We are searching for some object. We're doing some operation for T in our list, and we're performing it the length, how to say, dependent on the size of this list. If your size is n, then this loop will be performed n times. This will be performed also n times because it will go through all elements of your array. Then here we have on, here we have on plus on is 2on. We are not taking into an account the constants. Then the execution time of this selection is ON. The big O notation estimates the execution time of an algorithm in the relation to the input size. If the time is not related to the input size, the algorithm is said to take constant time with the notation O1. If the execution time of your algorithm doesn't depend on the input size, then notation will be O1. Here are some examples with animations for linear search and binary search, and you can analyze the big O notations of them. Some functions have execution time as logarithm. Which one of them? Assume that we have here binary search and it search a k in a sorted array. Each iteration in the algorithm contains a fixed number of operations denoted by C. Let's denote Tn, the time complexity for binary search. Without loss of generality, assume n is power of 2 and k is equal to log n. Since binary search eliminates half of the input after 2 comparisons, the time spent for binary search time complexity will be n over 2 plus some kind of constant. Here it will be n over 2 to the power of 2 and then n over 2 to the power of some k. This is performed like this, and if we will open this function, then we will have t1 times some kind of constant times 2 log n. It will be 1 plus c log n. The big O notation of binary search then will be log n times. Ignoring constants and smaller terms in the complexity of the binary search algorithms is O log n. An algorithm for the O log n time complexity is called a logarithmic algorithm. The base of the log is 2, but the k base doesn't affect the logarithm growth, so it can be omitted. The logarithmic algorithm grows slowly as the problem size increases. If you square the input size, you only double the time for the algorithm. The selection sort is, first of all, we have analyzed here binary search and found that the big O notation for binary search is O log n. For selection sort, the time complexity is O n square, because each time the time that we spend to find some to sort some algorithm, to sort some array, will be in the first we will go compare to n minus 1 times. Second, we compare n minus 2 times. Third, n minus 3, and each time you are sorting your algorithm to one element less. And when we are adding all these times, we will have the summation of numbers from 1 to n minus 1. It is n minus 1 times n minus 2 over 2, and when we simplify it, we will have that the selection sort time complexity is O n square. The algorithm with the O n square time complexity is called a quadratic algorithm. The quadratic algorithm grows quickly as the problem size increases. If you double the input size, time for the algorithm is quadrupled. Algorithms with the nested loop are often quadratic. In general, algorithms with the nested loop, they are quadratic algorithms. Here is the analysis of selection sort. Analysis of selection sort is written here. Here is insertion sort analysis, which is also an over 2. Here we have the analysis of Tower of Hanoi. It counts how much time it will spend to move the elements of into one tower into another tower. If you know the game of Hanoi Tower, if you will just Google it, you will understand this topic. And here is common recurrence relations, common times that are spent for some constant types of algorithms like binary search, Euclid, great common dependent. It takes log n time. For linear search, it takes O n time. For merge sort, it takes n log n time. Selection sort takes n square time. Tower of Hanoi, it takes 2 to the power of n times. And the recursive Fibonacci algorithm also takes 2 to the power of 2 or n times as complexity. If we compare common growth functions, the quickest one is O1, then comes log n, and then comes n, and then n log n, then n square, n cube, and 2 to the power of n. Or they are called constant time, logarithmic time, linear time, log linear time, quadratic, cubic, and exponential time. And if we will compare their growing rates, we will draw them in the graphic. We will see how they are changing that why. We will understand why O2 to the power of n is greater than others, because for example these functions they don't become much more related to the input size, but for this function it will be very high depending on the input time. Here are some examples and some case studies. I will just skip these parts. for you to study at home. This is what I wanted to explain you related to time complexity of the algorithms. And if you have some more questions, you can ask them on the practice time to your practice teacher. Thank you for your attention.